Hi, everyone. Today we're going to talk about lesson 10 on combustion reactions, one of my favorites. But first, we're going to talk about the answers to our double replacement reaction homework. So, taking a look at question number 4. When we figure out what our products are, we have barium, which is a 2+ charge, and phosphate, which is a 3- charge, forming barium phosphate, Ba3PO42. This ends up being a solid because of the rule about phosphates. Phosphates in general are insoluble. Our second product will be H+ and NO3- forming HNO3 or nitric acid. Balancing the equation should be pretty straightforward. Nitric acid, remember, all nitrates are soluble, so we label this as being aqueous. In example number 5, we had sodium acetate reacting with silver nitrate. Silver is going to combine with the acetate here to form silver acetate. And although acetates in general are soluble, silver acetate is an exception. And in this case, we're going to form the solid of silver acetate. And then our second product will be the combination of sodium and nitrate, +1, -1, so one of each. And that will be aqueous, both because group 1 elements and nitrates are both soluble. When we take a look at our 6th problem, we have silver nitrate combining with sodium chloride. They'll form silver chloride. Remember that chlorides are halides, and one of the exceptions to the halide rule is silver. So when a chloride is bonded to silver, it's a solid precipitate that forms. Our other product, sodium nitrate, +1, -1, that'll be an aqueous compound. Let's take a look at problem number 7. We have magnesium nitrate and potassium hydroxide. We form magnesium hydroxides. The rule for hydroxides tells us that it's going to be a solid. Potassium nitrate, of course, is going to be aqueous, group 1, and a nitrate. In question number 8, we have ammonium sulfide reacting with zinc chloride. It's going to form zinc sulfide, which is a solid. Again, the rule says that most sulfides are solids. And ammonium chloride, remember that ammonium compounds are always going to be aqueous. In number 9, we have a group 1, lithium hydroxide, reacting with hydrochloric acid. It forms lithium chloride, +1, -1, and then water. That's our acid plus base example, yields a salt and water. And then finally, in number 10, we have lead-2 nitrate and sodium chloride. That's going to form lead-2 chloride, which is a solid. That's one of the exceptions for halides, and sodium nitrate. Finally, let's take a look at our last 3 problems. So we have zinc acetate and cesium hydroxide. That's going to form zinc hydroxide, which is a solid, and cesium acetate. That's going to be a group 1, so it'll be aqueous. Ammonium sulfide and lead-2 nitrate, that's going to form lead-2 sulfide. That's going to be a solid. And ammonium nitrate, which of course will be aqueous, group ammonium compound and a nitrate, both of which are highly soluble. Finally, number 16, we have iron 3 sulfate and 3 barium iodide forming barium sulfate. That's one of the exceptions to sulfates being soluble, and iron 3 iodide or ferric iodide. And again, iodide is a halide. Iron is not an exception to the halide rule. If we look at our last 4 examples here, 17, 18, 19, and 20, the first one, notice, is a no reaction. We have chromium 3 bromide, which is an aqueous compound. Sodium nitrate is an aqueous compound. We form sodium bromide, which is also aqueous, and chromium nitrate. And of course, we know that all nitrates are aqueous. So I made this red on the homework just to remind you that this is in fact an example of a no reaction. Number 18, we have rubidium phosphate. That's a group 1, so it's soluble. We have a nitrate, so it's soluble. We form rubidium nitrate, +1, -1. That's going to be soluble. And titanium 4 phosphate. This is a solid. Again, that's based on the rule for phosphates. Here we have ammonium carbonate reacting with nickel 2 chloride. It's going to form ammonium chloride. That will, of course, be soluble. All ammonium compounds are soluble. And nickel 2 carbonate, which is going to be your solid precipitate. And finally, our last example, we have tin 4 nitrate. So nitrates are soluble, so that's why we have aqueous here. Group 1s are soluble, so potassium sulfite is going to be soluble. However, the combination of tin and sulfite is not aqueous. That'll form a solid product, and our potassium nitrate, which is aqueous. Let's talk about combustion reactions. So in a combustion reaction, we have something known as a hydrocarbon, which, as its name suggests, is made up of hydrogen and carbon and possibly oxygen. So we'll label this as a hydrocarbon. Reacts with oxygen. This will always be one of the reactants in a combustion reaction. And it always is going to form, for our purpose, carbon dioxide and water. These two will also always be our products. That makes predicting the products a lot easier because we already know that all of our products are going to automatically be carbon dioxide and water. Let's take a look at a demonstration of a combustion reaction. So the last experiment is a combustion reaction. So what we're going to do is we are going to combust a flammable gas. That same flammable gas that we saw, the same flammable gas that we saw earlier coming out of the gas jet, we are going to bubble into this beaker here. Now, the beaker, I should warn you, has a soap solution in it, like a Dawn soap solution in it. So the purpose of the Dawn soap solution is to create basically a vessel to hold on to the gas until we are ready to light it on fire. So I'm just mixing that up right now. Okay, at this point, I'm going to turn on the gas. So you can start to see the gas bubbling out of the tube on the bottom. So I'm just going to turn off the gas. Then we'll light this gas on fire. So you can try that once more. Again, we'll light this. I hope you enjoyed that. In that demonstration, we used methane, or natural gas, which is mostly methane. We combined that with oxygen in the air, and we produced carbon dioxide and water. Now, methane was a gas. That was the gas that I captured in those soap bubbles. Oxygen in the air is, of course, a gas. Same for carbon dioxide. And because this reaction took place at such an elevated temperature, a tremendous amount of heat was given off, we can also assume that water was above its boiling point and should also be considered a gas. Balancing this reaction, we have 1C, 4 H's, 4 H's, 2 O's plus 2 O's is 4, so we need to put a 2 in front of that. Full disclosure, methane and natural gas is very dangerous. Please do not try and produce the same reaction at home. Let's take a look at some example problems. As I mentioned earlier, the nice part and what makes combustion reactions so easy is that we don't have to predict products. We already know they're going to be carbon dioxide and water, both in the gaseous phase. So what it boils down to is that most combustion reactions are simply an exercise in balancing equations. So we have 6 carbons on the left. We're going to put a 6 in front of carbon dioxide. We have 6 hydrogen on the left. So we're going to put a 3 in front of water. Now, if we look, we have 12 plus 3 is 15 oxygens. This is one of those examples where in order to get a balanced chemical equation, we're going to have to double all of our coefficients. So There was a 1 here. We're going to make that a 2. There was a 7.5 here, which is why we had to double everything. We're going to make that a 15. The 6 will become a 12. And the 3 will become a 6. As I've mentioned previously, always go back and check your balancing. We have 2 times 6, or 12 carbons. We have 12 carbons. We have 2 times 6, or 12 hydrogens. We have 6 times 2, or 12 hydrogens. And finally, we have 15 times 2, or 30 oxygens. We have 12 times 2, that's 24 oxygens, plus 6 more is equal to 30. Let's take a look at our second example. So in our second example, we have what's called methanol, CH3OH. You don't have to worry about naming these. We form, of course, carbon dioxide gas and water. Now we're going to balance this reaction. We have 1 carbon, 1 carbon. We have 4 H's. 3 H's plus 1 more is 4. So we're going to put a 2 in front of the water to get 4 H's. Now looking at oxygen, we have 2 oxygen here, plus 2 more oxygen here. That's 4 oxygen. And over here we have 3. So we're going to need to double everything. So we're going to take the 1 here and make it a 2. In this case, we have 2 carbon dioxide now, because we need to make that a 2. And we're going to cross out our 2 in front of water and make that a 4. Finally, we have 4 oxygen plus 4 more is 8. We have 2 oxygen right here, so we need 6 more, meaning that we're going to put a 3 on the line in front of oxygen. Let's take a look at some of the homework problems. So to make things easier, I'm just going to go down the list first and write in all of my products. Okay, if we take a look at the first equation, we have 1 carbon, 4 hydrogens, 2 hydrogens. So I can put a 2 in front of that. That'll give me 4. I have 2 oxygens plus 2 more oxygens is 4 total. So I can put a 2 there. This equation is now balanced, so I can drop in 1s. If I look at the next problem, I have C3, so I'm going to put a 3 in front of carbon dioxide, H6, so I'm going to put a 3 in front of water to get 6 H's. So now I have 6 O's here, plus 3 more O's, that's 9 oxygens. I can't get 9 if they're coming 2 at a time. So again, I run into a problem where I'm going to have to double everything. This is very common when you're doing combustion reactions. I'm going to put a 2 in front of C3H6, so I now have 6 carbons. So I'm going to put a 6 here. I have 12 hydrogens. So I'm going to put a 6 here, so I wind up with 12 hydrogens. And now I have 12 oxygens, 6 times 2, plus 6 more is 18. So now I can go ahead and put that 9 right on the line. Let's look at our third and final example here. So we have C5H12. So I have 5 carbons. I'm going to put a 5 in front of carbon dioxide. I have 12 hydrogens. So I'm going to put a 6 in front of my water. Now counting oxygen, I have 5 times 2 or 10 plus 6 more. That's 16. So I'm going to put an 8 in front of O2 in order to get 16 oxygens. I hope you find that combustion reactions are a little bit easier than some of the other reaction types. Have a great week, everyone.